Why?
Because we're only like, you were 7 last time.
Yeah, but here we were like, I don't know, many. Anyway, so last time we stopped here, we solved an example on power flow. I think I signed the homework. The homework has an problem with 2 iterations. So it's good for me. It's good for you to go through, and I will ask Adil as well to do something like a small 2 iteration problem as well in the recitation. Yeah. But again, generally the only thing additional thing that you do with a 2 iteration problem is find the new estimates, right? You will find the new estimates for your values of voltages and angles, right? So, because at the beginning you have to start by finding these power mismatches, or I call them sensitivities, right? So these power mismatches is the difference between the power that you know at a specific bus and the right-hand side of the summation of the power that's in the power flow equation. So you start by plugging in your current variables, values for voltage and angle, find the power mismatches. The power mismatches are small, all less than your convergence criteria, you stop. They're not small, then you have to find all the power mismatches, put them in a vector, and then you have to find which is this vector, and then find the Jacobian matrix, invert the Jacobian matrix and pre-multiply by the power mismatches, and then you will be able to come up with your changes in angles and voltages, and then use those changes to calculate your new angles and voltages by adding them to the previous angles and voltage from the previous iteration. Really, it's simple. There's nothing more to it yet. Okay. So this is where we stopped last time. We sort of calculated an element of the vector of the power mismatch vector, and then we calculated an element in the Jacobian matrix. Okay. So I'm not going to go through and calculate everything. In the homeworks, you have something like that where you can go through. The nice thing about Power World, as I said, is it uses this Newton-Raphson method to calculate the power flow. So this slide shows you actually how to check your answer. So this is the same example. This 5-bus example is the same example that we have up here that we've been playing with. It's the same system that we have up all the way up here. This 5-bus system. We solved it manually right now, right? We came up with the Y bus, then we came up with then we wrote the power flow equations. We decided what variables are there, what variables are not there, and we came up with the power flow equations. And then we figured out how to build the Jacobian matrix and calculated some elements in the Jacobian matrix. And these elements to calculate in Jacobian, we then went ahead and calculated power mismatch vectors at iteration 0, and the elements of the Jacobian matrix at iteration 0. We did that, right? Is there a way to check your answer, right? So then the good way to check your answer is to actually do the simulation. So if you go to this slide that we just had displayed here, what it says is to see the complete convergence of this case, open Power World simulation. So this is example 611 in your Power World examples. If you go to the Power World examples files, this is example 611. Select case information, network mismatches, and network mismatches are the delta P's and delta Q's. So they will tell you the delta P's to see the initial mismatches. So they calculate the initial mismatches based on what you say is going to be your starting points for your angles and voltages. And case information solution. If you go to case information, solution details, power flow Jacobian, and you can view the initial Jacobian matrix. Right, so you can actually do that. And if you go to if you want to step through and look at each iteration, you go to and in the tools ribbon, select solve, single solution. Single solution is single iteration. Full Newton. Why full Newton versus something else? I will talk about something else now shortly. But basically, we're using the full Newton method. So we're using the full Newton method, and this can iterate through the Newton method. So ordinarily, this selection will perform a complete Newton-Raphson iteration, stopping only when all the mismatches are less than the desired tolerance. However, for this case, in order to allow seeing the solution process, the maximum number of iterations has been set to 1. So we iterate only 1. In this example, the maximum number of iterations, you set the maximum number of iterations that you allow the program, the software to do. It's a software. How many iterations you allow to do is up to you. So if you do that, it's set to 1 in this example, and you will actually be able, and if you continue to do this, solve single solution, it will give you a second iteration, third iteration, fourth iteration. So, and it will give you the exact same values that you will get as a designer of the system, or if you solve it manually, right? So you can try this with a small 2x2 system, for example, if you want to study for the exam. How would you study for the exam for this chapter? I would construct a 2-bus system and do this: one load bus, for example, and one bus with for 2 or 3 bus system. Construct one load bus and one PV bus and one slack bus, right, in PowerWorld, and solve it and iterate and look at the Jacobian and look at the power mismatches. And that's it. You're done with the chapter study. What else do we have in this chapter? Right? It's just a power flow problem. Really, it's very systematic. There is nothing. I cannot bring tricks. There's no tricks to it. There's no really. There's no tricks to it. Power systems is very systematic, right? So if you want, this is how you would solve. This is an example of how you can study, and this example is solved for you. But this is a 5-bus system. If you want to go and make a 5-bus system, you can do that. I prefer to do it. If you want to do a small system, 3-bus maximum, it's easier to solve manually, and then with a calculator, and then with PowerWorld. And then this is the only thing you need to do for studying this chapter, really, for the most part. I mean, there's some theoretical stuff that we will cover still, but this is the core of this chapter. Okay. So, and this is the solution manually that is also extracted from PowerWorld. So if you solve it manually, these are the solutions that you'll get. So I recommend doing this exercise. Go through this exercise and build a 3-bus system, or do it for this 5-bus system. Because for this 5-bus system, you can calculate. You don't need to calculate all the elements of the Jacobian matrix for the first iteration. You can calculate a few elements, but maybe take the results from the PowerWorld after the first iteration, and then calculate a few elements after the first iteration, right? Because I can give you results after the first iteration. I can give you the values of voltages and angles after the first iteration, right? And then you can go back and calculate the Jacobian matrix after the first iteration, and etc., etc. So you can do this by yourself using PowerWorld. Okay. That being said, we now want to talk a little bit about how power flow is controlled. We sort of discussed this before, but we're going to put some equations to it and draw some phasor diagrams, etc., etc. So when you played with PowerWorld, you saw that fine. Each bus has voltages and angles, and anytime there's an angle difference between buses, even though the voltage magnitudes are the same, of course power will flow, right? And if you look closely to some of the simulations, for example, I don't know if it will be clear here. We don't have no, we do. It's not. We don't have the angles. For some reason, the angles are not shown in this simulation. But let's see if they are shown in the solution, the output bus output data for the system given in this one. Angles in degrees. So let's see. So bus 1 is a slack bus, so it's 1 angle 0, of course. Let's see what's happening at bus 2. So where is bus 2? Bus 2 has the big load, right? So the biggest load is at bus 2. So and there's no load at bus 5, and then there's no load at bus 4, right? So the big load is really at this bus, right? So we would expect that even though I'm controlling the voltage to be 1 per unit around the system, right? We would expect that the angle between bus 2 and everybody else's angle to be significant, right? And everything, and we're actually measuring everything with respect to the slack. So we're actually taking the absolute angle at this bus, so delta at bus 2, right? This is what we're solving for in the power flow equation. So we would expect to see the angle, the solution, being the angle at bus 2 versus the angle at the slack bus, for example, to be very different, right? So and that's what we have from the solution here, right? The rest of the buses, fine. There's power flowing through the buses, right? So you expect, so there is power flow from bus one to bus, bus one to bus, let's say, bus one to bus five. There is power flow there, and there is power flowing from bus three to bus four. So you would expect some angle differences here. There will be some angle differences here, but there is no huge load at that specific bus. So does this make some sense? Do the angles make some sense now? The fact that we have large angle difference, large angle at buses where there are large loads, right? So you would actually, it makes a lot of sense, because when you look at when you look at the manual solution of these systems, you will see, and when you look deep at the equations now, we will see that real power flow and angle difference is very correlated, and that's from the basics of how a synchronous machine operates. Synchronous machine or a synchronous generator, you supply mechanical input power, right? What does this mechanical input power do? It turns the generator, right? When you turn the generator, if there's no load, right? If there's no load, if you're putting torque in and there is zero load, and you forget about the friction of the bearings and all of that, okay? If you put torque in and it's a frictionless, lossless system, so what's going to happen to that system? Just a rotor levitated in air, you apply torque to it, right? You apply torque to it and it's lossless, and there's no load on it at all, and it's weightless and everything. Right? So what's going to happen to that rotating mass? It will accelerate forever, right? Theoretically speaking, it will accelerate forever, right? But of course, because of the friction and stuff like that, of course, it's not going to accelerate forever. There will be acceleration, and there will be a limit to that, right? But it will be accelerating. It will continue to accelerate as much as possible, right? But if you connect an electrical load to it, right? If you connect an electrical load to it, you're doing what? Then you have current flowing in a conductor in a time-varying magnetic field, which is a force, which creates a force on that conductor, right? This force opposes the force that created the motion, right? It opposes the torque that was placed on that generator, right? So if a generator is accelerating with respect to another generator, it means that the angle of the shaft of this generator that's accelerating is going to lead, or lead the angle of the shaft of the generator that is loaded. If I load this generator, what's going to happen? It will, its angle will be in synchronism or closer to the other generator that's working with it, but that is already currently supplying the load, right? So angle differences are really directly proportional to real power flow. Okay, so and that's why you see angle differences here. So the other thing is, look at the voltages. So that's the all the other angles are sort of in the close to zero. Fine, they're for bus 5 and bus 4, they're higher than yeah.
So like this 22 corresponds to both the power, real power and the reactive power. It's the power angle, right?
It's a power angle of the generator, okay, and the angle affects both real and reactive power, but I was going to explain something now that will help will answer your question. Then we're going to do the phasor diagrams later. So for now, let's sort of, okay, if you go back to our problem here, we had real power of 800 megawatts versus reactive power of 280 megabars, and let's look at what was really affected significantly at bus 2. What was really affected significantly was the angle. The voltage was dropped from 1 to 0.8. It was dropped. It did change, right? But it did not change as significantly as the angle change, right? But now let's look at the other buses. The other buses, then the angles did not change significantly from 0, because there is no real power loads at these buses, okay? So it seems like real power and angle are more correlated, right? And then look at the voltage of the other buses. All of the voltage of the other buses, did they change much? The voltage of the other buses are all closer to the 1 per unit versus the voltage at bus 2. So, and at bus 2, what we have in addition to real power is also some reactive power being drawn there, right? So we will see from the equations later as well, shortly, that reactive power and voltage magnitudes are directly related. And we saw that before from the idea of power factor correction, right? When you did power factor correction, you had an induction motor, for example, and you put a capacitor across. Before putting the capacitor, that induction motor was drawing all the reactive power from the utility, right? So there was a reactive voltage drop across the line that's coming from the generator's side. There was a reactive voltage drop, right? But now I put a capacitor right across the load, right across the induction motor. What happened? Exactly, it's generating reactive power locally for that induction motor, meaning the reactive power is not coming through the line, meaning there is no drop across the line due to the line's inductance. Right? So what we did was with capacitor, what the capacitor did was play with the voltage. Right? So it allowed the voltage not to be dropped across the line between the generator and the load. Does it make sense in this case? I don't care what the rating of my induction motor is, but what I did was play with the voltage in this case. When I put a capacitor, when I put a pure capacitor, to supply the local reactive power, I don't have the drop across the line. What is this? This is my line's reactance. Current was flowing through this system. This is my load in this case, for example, and then there's a voltage drop due to this line's reactance. Because current here needs to go supply this inductor. This inductor is actually consuming only reactive power, right, in this case. So this current is only reactive in this case. So what happens now, what I'm saying is that right now what I'm doing is I'm putting a capacitor right across this load. So what is this doing? This is, let's say I tune this capacitor, select the proper size of this capacitor at the power frequency so that omega L is equal to 1 over omega C, right? If I select the L and the C such that this is happening. What does this mean? It means that my system looks like this only. I only have this inductance left, this line inductance left. Right? So I do not need to, as if I don't need to supply the load anymore. Right? The load is now being supplied locally. But of course there's no load that is only pure inductor. There's a resistive component. But basically what happens is now I do not need this reactive power to come. There's no need for reactive power to come because this looks like a pure resistor in this case. Let's say this is a RL circuit. Right? This looks like a pure resistor in this case. I do not need to supply any reactive power to this anymore. I just need to supply the real power that it was consuming. Right? So what does that mean? That means that less current is going to come from my supply to feed the load. If less current is coming, that means the voltage drop across this is less. So I've affected the voltage magnitude. Right? And we will see from the equations these two characteristics, but it's also clear from here. If you look at what's happening here, you can actually, without looking at the system, you will know that, okay, at bus 2, I probably have a reactive load because voltage dropped significantly. And at bus 2, I also probably have a big real load because angle difference between it and the slack bus is quite significant. Right? At the rest of the buses, seems like I don't have any reactive loads. Or maybe small, very light real loads are there at the buses, or nothing. Okay, that's what you get from the numbers here. Okay, so it seems like angle differences are controlling real power flow, and voltage differences are controlling reactive power flow. That's what seems to be happening here. So actually, before we do that, let's look at the equations that prove this, and then we can go back to this. So let's look at the power flow equation, the derivatives of the power flow equations. let's for example look at these. The derivatives of the power flow equation, real and reactive power. Okay, so in this case, what is this differential telling us? Remember, these are what we have. We're filling in the Jacobian matrix with, right? These are all the elements in the Jacobian matrix. So what this tells us, and remember when we saw that two buses are not connected, we sort of put a zero in the Jacobian matrix, right? So if power, if we have, bus 1 is here, bus 2 is here, and bus 3 is here. So bus 1 and bus 3 are not connected, for example, in this case. So dp1 by d theta 1 was equal to 0. What does this mean? It means that there is no change in power when there are changes in angle at bus dp1 by d theta 3, sorry. There is no change in power at bus 1, real power at bus 1, versus when changes are occurring in angle at bus 3, right? There's no direct relationship between them, right? They're related through bus 2, so there will be changes at bus 2, and these changes at bus 2 will affect bus 1. But there is no direct relation between real power change at bus 1 and angle change at bus 3. They're related through 2, right? So these things that we fill the Jacobian with have a lot of physical meaning, right? It's not, okay, I just filled stuff in the Jacobian, right? They are actually physically telling us what's happening in the system. And that's the reason why we saw these numbers, come out. And we'll see why the relationship between P and angle and Q and voltage, why these relationship exists. So what did we say is a good way to start your system? For the power flow problem, what are the good starting values for angles and voltages? Angles all 0, and voltages all close to 1, right? So angles all 0 and voltages all close to 1. So if I put angles as 0, right, in the Jacobi matrix, right? So what happens to sine 0 is? Sine 0 is 0, so this goes away. Also, what other thing did we assume in a power system? Are we going to design a power system such that we are operating inefficiently and burning power in the cables? No. We're typically going to design and select cables that have very low resistance, if we can. Of course, this mainly applies to transmission and stub transmission and maybe distribution before it comes inside the building. But inside the building, you don't have space to put a cable this big, right? I cannot put a cable this big behind the wall so that I can reduce the resistance of the load that I'm putting, of the resistance of the cable that's going to feed the load connected to this load in the room, right? So here I don't have a choice. At the distribution level, it's tough. Things change, actually. The physics change at the distribution level. But at the transmission level, the transmission company, the utility company, needs to make sure that it's supplying as much of the power as it can to the consumer. So it wants to optimize or improve its efficiency as much as possible. So it will select transformers, cables, etc., such that the resistance is almost zero. Almost zero. Right? It will select, the resistance is almost zero. We neglected. Remember, in the transformer, we would just put a series inductance. In the cables, we put a series inductance, right? We were ignoring everything. We were ignoring the series resistance because it's small at the transmission level, right? So if we do that, if R is 0, remember that admittance is equal to G plus JB, which is equal to 1 over Z. 1 over Z is equal to 1 over R plus JX. If you multiply this 1 over R plus JX, if I multiply by R plus JX over R plus JX, what do I get? I get R over R squared plus X squared, right? R minus? So if I multiply by minus JX, what do I get? R squared plus X squared? right? So I get r minus jx over r squared plus x squared. So this is now g, right? And this is my b. B is minus x over blah, 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 right? So, which means if r is 0, it means that g is also 0, right? This is g, right? This is the conductance term, right? So g is also 0. So if r is 0, then g is 0, angle is 0, and v's are 1, right? So angle is 0, this went away. I'm left with, you know, I'm left with this. B is not 0, so this exists. So there is a, so the relationship between changes in power and changes in angles have a value. It's still significant. It has some significance. But now let's look at this one. Sine is, angles are 0, so this is 0. What also did we say is 0? The g's. The r is 0, so that means the g is 0. This is the rectangular form, written in rectangular form. So that means this is also 0. So what does this tell us? It tells us that the relationship between power, changes in power and changes in voltage is not very significant. In a system where these conditions apply, not again, it exists. There is a relationship between power and voltage changes, right? But it's not very significant in an unstressed, highly efficient system. That's what this means, right? But the power flow problem considers everything. The power flow, when you solve the power flow problem, you consider everything. But you know, when you solve the power flow problem and you look at the numbers, you need to understand what's happening, right? So why is this, okay, at a bus where there's a load, I see big angle because of this phenomena, right? At a bus where you see big changes in angles, you expect to see big changes in real power because there is a strong relationship or strong coupling between real power and angle. But there is no strong coupling between real power and voltage. There is no strong coupling. It exists, but it's not very strong. Same thing with reactive power. Okay, we said G is 0, so this goes away. Sine is 0, so this goes away. Right? Under these assumptions, which means that reactive power and angle changes, reactive power changes and angle changes are not very strongly correlated. But reactive power and voltage changes, this is 0, but this exists. Right? So in your power flow equations, the conclusion of this is real power changes are sort of something you can easily gauge by looking at angles. And reactive power changes are easily something you can correlate with by looking at voltage differences. Okay, so you will easily know, okay, here there's a reactive load, here there's no reactive load, here, right? You will know this by looking at the numbers on your screen from after conducting a power flow of the system. Okay? So does it make sense? Okay. Now that I've said this, we can now look at how we control a generator. So now that we've said this stuff, we want to see how do we control a generator. So how would we control a generator then? If I want to change, if an additional load is added and this load is consuming more real power, what do I expect to do to my generator? Exactly. Put more mechanical power in. If I put more mechanical power in to accelerate, it will advance the angle with respect to the other generators in the system. They're all operating at 50 hertz plus minus, right? But I will speed this one up. I will put more mechanical power. Put more mechanical power, I will be able to give more angle. My load angle will increase. Load angle increases means I supply more real power to the system, right? So what else do I need to do to my generator? How else do I control my generator? This is one way I control real power. How do I control reactive power from the generator then? We said real power and angle. So real power and angle. We said reactive power and voltage. So I need to control my generator's voltage. So how do I control my generator? If you have a machine, a synchronous machine, How do you control the synchronous machine's terminal voltage? For people that took 338 or are taking 338, how do you taps what? Taps in the transformer. Transformer taps is one way to control system voltages, yes. But I'm talking about the generator. Yes, so let me go here. So these 3 points. The following means are used to control power system flows. Well, one, prime mover, which is the input mechanical power, and excitation control of generators. This is where the answer is, right? So in a synchronous machine, you have a field winding, right? This field winding is an electromagnet, right? If the electromagnet is strong, meaning you put more current in that field winding, what happens? It's like having a strong magnet there. You have a strong magnet there, and you put some windings close to it, and you spin that electromagnet. You will induce voltage in that winding, in these windings, right? In a time-varying magnetic field, you put a turn, then voltage will be induced at the terminals of this turn, right? The number of turns will not change. This turn will not change, but the voltage at the terminals of this turn will change if you change the magnet that you're using, right? If you use a stronger magnet versus a weaker magnet, and you spin the same magnet in the same speed, then the voltage across the turn that is close by will change. So the way you would control the generator's voltage is by controlling the excitation, or the field winding. It's another fancy name for the field winding current, right? How many people took 338? You covered this, right? This is very important, right? It's really important, yeah. So the generator, actually, any generator has two main control circuits. One control circuit to control field winding current, which is basically a control of voltage, back EMF voltage that's induced across the turns, which is another indirectly controlling reactive power in the system. Right? So this is the way you would control reactive power system is by controlling the excitation of the generator. And we'll draw the phasor diagram for a simple equivalent circuit like that. Right? The other main control circuit is what is called prime mover or governor control circuit. The prime mover or governor control circuit is what is controlling the input torque to the generator, which is eventually controlling the angle between that generator and its neighbors. Right? So these are the two main control circuits in the system. Okay? How else can you control power flow? Besides the generator, you can of course put in capacitors like we just discussed. Right? Or you can put in inductors. If you have a leading power factor system, sometimes you would need to put inductors, not capacitors. And sometimes you don't put fixed capacitors and inductors, you put power electronic based capacitors and inductors. So you connect these capacitors and inductors through power electronics to the power system when you need to. Okay? So this is how you would use them. And then the other way to control, of course, voltages and angles, because again, what we decided is we're going to be, if we control voltage, magnitudes, and angles, then we're controlling real and reactive power flow. That's how we control real and reactive power flow. So the other way to do this is control of the taps of the transformer, or use phase shifting transformers. We didn't cover we just talked about the star delta as a phase shifting transformer, But there are transformers that can apply many other phase shifts, and you can make these things change with time as well. So, but we didn't cover many of these. They're not very common. So, but that's another way to do it. But at the end of the day, you're controlling voltage, magnitude, and angles. Right? That's how you would control real and reactive power flow. So let's look at the simple equivalent circuit of a generator connected to a voltage, a bus. And again, I think the way that it's referred to in power system terminology and in 338, Dr. Aitam probably talked to you about an infinite bus, right? Did you hear the word infinite bus before? What does infinite bus mean? Infinite bus means just a big system, right? A big system that has 100 generators, for example, that are synchronized. All these generators are at similar voltage and running at similar angles, right? You small new generator coming into synchronize are not going to affect all of these. They will probably affect you. I mean, the power that they are providing is much bigger, right? So we will assume that a new generator wants to come in and synchronize with the grid. I will assume that I have to meet a certain voltage and angle requirement, right? That's how you synchronize in the experiment in 338. You brought in a generator, You made sure that the voltage and frequency were exactly the same, and then you close the switch, right? So that's synchronizing to an infinite bus sort of example. So, and that bus is your reference. So let's say this reference has a voltage V, angle 0. Sorry, this is what, outcome of a PDF conversion, right? It's not there. So I looked at the PDF, the PowerPoint slides, and there was an angle actually. But so I will see. I will create a PDF again using maybe Mac, or I don't know. The PDF creator was poor, so it changed the angle sign to this D sign. Yeah. Okay, so this is V, angle 0. Okay, so I have a voltage bus here that I need to synchronize to, and I have, this is the equivalent circuit of any power source, is an ideal voltage source and an impedance in series. We will ignore the resistance of the generator, because typically we have low resistance in all power equipment, so we will ignore the resistance. So it's a voltage source with a reactance in series. So I want to make sure that I'm controlling real and reactive power. The way I would control real and reactive power is by controlling the armature current that I have flowing in here and its phase angles. That's really how I would do this control, right? And for me to supply the reactive power, the only control I have is this voltage magnitude and angle. Or the only controls that I have are actually, what controls do I have on controlling this current? The only control I have is this voltage as a magnitude and its angle. This angle is the power angle of the generator, right? This is my generator, right? This is my equivalent circuit of my generator, right? This equivalent circuit of the generator is nothing but a voltage source with an angle. And these are my two things that I'm controlling in the generator. The voltage source is the excitation, and the angle of this voltage source is my power angle of the transformer, of the generator, or the delta that we're calculating in the power flow problem. Okay, so that's how we will perform the control. So if I look at this circuit, the current is equal to what? Current is equal to this voltage divided by the impedance, or this voltage minus this voltage divided by the impedance. If I want to look at this current here, it's this voltage minus my reference voltage, or my terminal voltage, divided by this impedance here. So it's this voltage, my generator voltage, as a magnitude and an angle, minus the terminal voltage divided by the impedance of the generator. And power, complex power is equal to, that complex power that's delivered by the generator. So this is the terminals of the generator. This is where delivery is happening. So the terminal power, the complex power delivered by the generator is equal to the voltage at the terminals of the generator multiplied by the current conjugate. Current is what I just calculated here, right? This is what's being delivered to the power system. So it's VT, V terminal voltage, times I conjugate. Which I? It's this I here. So I took this I, changed the angles, so that so I can account for the conjugate of the current, right? So, and then what do? I split the real, and this is a complex number. I split real and reactive terms, and I end up with an expression for real power and an expression for reactive power. What do we see in the expression? We see that this is sinusoidal. Remember, please note, this is sinusoidal and this is cosinusoidal. Let's see what the sinusoid looks like and a cosine looks like. So this is a sine wave. And half a sine wave, and then this would be a cosine. Okay, so this is the peak value or something. Sorry, no. Not as nice, but it's for a reason. I will show you why. This is a little bit down. I mean, I drew it a little bit flat because of something I want to explain here. So this is, sine, cosine. Okay. So what's happening to a sine wave at small angles? Increases significantly. It was 0 and it jumps all the way to 0.8, for example, at what, 30 degrees or 40 degrees, something like that, right? How about a cosine wave? Especially the way I drew it. at small angles. Yeah, there's not much significant decrease, right? But even if you draw it properly, there's not much significant decrease at small angles. Yeah. Okay. So look at, and then let's look at the equation. So real power is equal to some magnitude, which includes the voltage, by the way. And then remember, I can only control EG as a magnitude and then angle. These are the two things I can control. That's it. These are the only two things I control in the generator. So this equation has both. This equation also has both, right? This equation has both of them. But let's look at the real power equation. The real power equation, there is the sine term is there, right? So small changes in the angle will affect the real power significantly, right? I don't expect that the voltage magnitude should change considerably, right? I do not expect, I mean, I'm not, do I expect, remember what we were saying, that voltage magnitudes are going to be directly correlated to, we saw that in the solution, all voltage magnitudes are going to be close to 1, right? That's what we said about per unit. And then when we saw the example that we went through today, we said that, we saw that all the buses had voltages close to 1, but that one bus that had the largest reactive power, okay, voltage was like 0.87 or something like that, right? So voltage don't change significantly. And I will look, and we will see why from the phasor diagram. I mean, yeah, from the phasor that you have a voltage source here, and this is E, G, and this is V. Do you expect a significant change between EG and V? This is a bus. There's not significant changes between EG and V. They're very close to each other, right? So you don't expect. We will see how E changes and why to control reactive power. We will see how it will change in the phasor diagram, but we don't expect significant changes in E in the generator, right? So E will change, but not significantly. But the angle will change. Will not change significantly either, right? We don't expect one generator to be 100 degrees out of phase with the other generator. When we solved when we looked at the solution for the power flow problem, what was the angle of the highest bus at the highest bus? 22 degrees, right? What is the maximum angle? Okay, what happens? Sine has a maximum value at 90 degrees, right? What happens to the angle after 90 degrees? The real power, sine will decrease, which means real power will actually decrease. So actually, if you try to give more torque or a prime mover input, you burn more steam, burn more gas, or whatever you want to do to put more torque on the shaft, and the generator angle advances close to or beyond 90 degrees, you're actually trying to put torque, and you're not, and providing less electrical output. What does that mean? What's going to happen to the generator? Remember when we had no electrical output or load on the generator, what was happening to it? It was accelerating. And that's exactly what's going to happen in this case, right? You're going to put more torque. You're saying you're going to burn more steam to put more torque. And then my electrical load also decreases. So the generator keeps increasing, accelerating. It will fall out of synchronism, right? So you do not operate, and this is happening at 90 degrees. Right, do you want to operate close to 90 degrees? For sure not. You're operating way below that. So, because there's a steady state. Everything we're talking about is happening in steady state, right? But what if Qatar Steel comes on board? A big load comes on board, right? The delta changes, right? This is a physical system, right? Who took 420? You took 420, you are taking 420, it's an LR circuit, right? At the end of the day, generator is an LR circuit, right? Dr. Hazem probably gave you an LR circuit, put a step response. What happens to the current? In steady state, what happens? L is a short circuit, and the current will go to the steady state value, right? Steady state. How about transient? Yes, depending on the value of the inductance, the system can go like this. This is what will happen to the system, right? So any system can be, or if you properly design your controller, which is what you should learn in 420, then you can, if you want to, make it look like something like this, right? So you can have the current not overshoot. It's an overdamped system. But what's the problem with overdamped systems? 420? slow. Your cutter steel will come on board. It was like, okay, wait. You cannot, right? You have to be fast, right? You have to be fast, right? These loads are coming on board. You have to supply the load. Otherwise, generators will slow down, frequency will deviate. You don't want that to happen, right? So you have to be as fast as possible. So you have to be as fast as you can. And at the same time, try not to have significant overshoots, etc., right? So that means when you have a load, this angle will change and bounce back and forth until it stabilizes at its steady state angle that we're talking about, right? So you do not want to operate at 80 degrees. You have a big load coming on board and the angle will oscillate a little bit, get close to 90, it falls out of synchronism, right? So you're typically, these angles are, maybe less than 30 all the time, right? So that's something you need to consider. So these things, so what was happening here is, go back to this equation. We see now the relationship between, we saw the relationship between real power and angle before in the power flow equations. When we looked at the Jacobian differentials, we saw the relationship. Here again, we see the relationship, right? The angle changes are significantly going to change real power, right? Voltage changes are not significant anyway, right? Because they should not be significant yet. So if there's a change in, okay, so that's, then if you look at reactive power has the cosine here, right? Cosines for small angles, less than 30 degrees, is what? Pretty much fixed. Small changes, right? So angle will not really affect reactive power much, right? But so in that case, we have to play with the voltage to affect it. That we don't have any other controls. Okay? So, and these of course is equations that we derived in. This is single phase, right? So you can also multiply everything by 3 and derive the 3 phase, and that's what we have in the next slide. But again, just to note, if you want to control real power to be a fixed value, right, and change reactive power, we know that for us to control reactive power, I will change E. If I change E, it's also changing the generator voltage, the real power, right? So I will have to also play with delta a little bit to be able to supply a fixed reactive power. But the changes will not be significant in delta to control reactive power. So they are related, as we said, from the Jacobian matrix equations. They are related, but not very significant relation between reactive power and angle. But there is a relationship, right? And this is what is described in this paragraph here. Any questions on this? Good. Yeah, what I just talked about is described in these, this stuff here. So read over it, and if you have questions, let me know. And then this is the same equation but derived. I put 3 here, right? It's still a single phase equivalent circuit. So I is still generator internal or back EMF voltage minus terminal voltage divided by reactance in single phase. But for 3 phase power, I multiplied by 3, right? So the only thing that's the only thing that changed from 3 phase to single phase. And of course, and we talked about sine delta being 90 degrees, delta being 90 degrees, so sine delta being 1. So this is sort of the maximum real power that can be produced by the generator. So there is a maximum limit that the generator can produce. Yeah. So any questions on this? We're good? So before I go to this, let's look at the equivalent circuit. So let's look at what happens to the phasor diagram, and let's look at the generator capability limits here. Okay, so I have a voltage source here, E with an angle delta, a reactance, and a terminal voltage that I have to meet, or I have to sort of synchronize to, and so this is where my load is and where I'm supplying the power. Okay, so and the single line diagram for that is the following. This is E here, V here. This is IA, this is JXS. And this is called generator synchronous reactance, right? If you remember from 338, I think Dr. Haytham also called that They lumped the effect of the armature reaction and the inductance of the stator winding and called that the synchronous reactance of the generator. So that's JXS. A simple equivalent circuit, voltage source with ideal voltage source with a reactance in series. So this is the generator. We want to see how the phasor diagram of, we saw the equations and how real and reactive power are controlled. So let's see how to draw the corresponding phasor diagram. Yeah. So I will start with my terminal voltage, because my terminal voltage is what will be fixed, right? I need to synchronize to that. I will call this VT angle 0, right? So starting from here, how would I draw E? I will have, of course, this is what? This is my terminals of the generator, so it's like having a load here, right? So this load will have some current, right? This current, will it be leading or lagging? Leading or lagging, depending on the load. It's a load, right? So typically, yes, it's lagging. So let's draw the current here, armature current, the IA for armature current. So IA is here, and this would be lagging by some angle theta degrees, right? So if I would like to now I can go back and how do I draw the E, the generator's voltage? Because this is the current I need to supply. I'm sort of reversing the process here, right? I already supplied the current. I assume that I already supplied the current, which means I already supplied some real and reactive power. What is the corresponding voltage and angle? I can go back to the equations, but I can also draw this on the phasor diagram. So what does the phasor diagram look like? I will take this voltage and then multiply the current by this reactance, and then I will be able to calculate E with its angle. Correct? So how do I draw this voltage drop? I will have to take this VT, add it to this voltage drop. How do I draw this voltage drop? This is voltage drop across an inductance, right? And this is the current that's in the inductance. So the current in the inductance lags the voltage drop across the inductance by 90 degrees, right? This is the current that's actually flowing to the load, but it's actually flowing through this inductor, which means it's the voltage drop here is IA times JIA times XS, right? So this JIA times XS, I want to add it to VT, right? So this JIA times XS looks like what? This is the current. The current will lag by 90 degrees. So the current, the voltage is somewhere here, right? This is 90 degrees, right? This is the voltage. But I want to add it to VT. So I will add it to VT this way. It is perpendicular. So add it to VT here. This is the magnitude of this is IA times XS. Do we agree? And this is the voltage drop across this reactance, which means that E is from this point to this point, right? The sum of the voltage drop across the reactance plus the terminal voltage is equal to E. E is this is E, right? For this condition. Everybody's okay with this? And what is this? That's delta. That's your power angle of the generator for this specific condition. Okay. If this angle between this point, this phasor, and this phasor is theta. Okay. And let me draw this line here, up here, parallel. Just draw a parallel line to this. Now, what is this angle? And hence, what is this angle? Take these two and rotate them. Right? Then what is this angle? Like take VT and put it here. Right? And where will I fall? Here, remember this is perpendicular. This voltage here is perpendicular to this, right? So I will take this VT now and rotate it by 90 degrees. So this red waveform and this red waveform should be in phase, right? If I take this VT and this IA and just rotate by 90 degrees. I drew this 90 degrees from this, right? So that means that VT and this phasor here will be superimposed across on this one, on this line, this parallel line, this horizontal line, and that this angle will be theta. Is everybody okay with this? Okay, so if this angle is theta, and I draw a perpendicular to this, right? Like geometry class now, right? And then let me extend this a little bit. And I want to know what is the magnitude of this. What is the magnitude of this in terms of IA, XS, and theta? Exactly. So it's IA times XS cosine theta, right? So remember, what is real power equal to? Real power is equal to, in any system, V or, yeah, S cosine theta. So real power is equal to S cosine theta. Some magnitude cosine theta, right? And this magnitude is sometimes is V times I cosine theta or S cosine theta, whatever. So this here, so basically that real power is proportional to it. This is a proportionality constant. This is a constant, some constant K. So real power is actually proportional to cosine theta. Do we agree? Proportional to it with some constant, yeah. So this is actually proportional. This space here is proportional to the real power here. How about if I do this? If I now increase the load current, and this becomes my new IA, what's going to happen? I have to extend this, right? The voltage drop will increase, but the angle will not change, right? So the voltage drop will increase, and this angle theta will not change. So this voltage drop will increase, and the new E will be here. This is E2. Of course, there's a delta 2. Do we agree or not? There's my drawing, of course, doesn't show that right here, but it's because I drew it by hand, right? So the delta 2 exists. But is there a big difference between delta 1 and delta 2? On this drawing, doesn't. But if you look here, we said delta is small anyway. So this seems to me this is a good change of delta compared to what I'm going to show next. Yeah. Okay. So this is a change in delta, right? It's also a change in E, right? But E changed from, this was the radius, and now this is the radius. There's some change in E. Compared to the magnitude of E, the change in E was not very significant. But compared to the size of delta, for example, this was the original delta versus this is the new delta, right? If you look at the ratio of this versus the original delta versus the ratio of this new change in E versus the original E, there is a much more significant change in delta than there is a significant change in E. And if I draw the same perpendicular, I know that this is now proportional. This distance here is proportional to real power. So the real power increased. Reactive power, did the reactive power change? Reactive power is based on the angle between voltage and current, terminal voltage and current. The angle did not change. So I did not change reactive power. I maintained reactive power. When I maintained reactive power and increased the active power, I had a more significant change in angle versus voltage, right? But there was still a change in voltage, right? So I still had to change voltage with some magnitude according to the equations that we had, right? There is small change in V, but angle change. So this is called the constant power line. Constant power line. Okay. Okay. Something else that's important is we'll do the reactive power change now. But before we do that, remember everything has a rating, right? Every piece of equipment has a rating. So an electrical machine will have a rating based on what? Basically heat and magnitude of voltage. Do we agree? It's heat. I mean, any electrical apparatus, a transformer, right, or a cable, just easy. I mean, two cables next to each other. I want to supply a load, and I want to. This load doesn't care how much current it consumes, but I want to put these two cables next to each other to supply this load. What's my limit? My limit is how close I can put these conductors next to each other without insulation. Or if I'm going to insulate them, then I have to make sure that the insulation will withstand the voltage, right? That's one condition. How about the other condition? The other condition is, okay, these cables are in ambient condition. Ambient condition is 50 degrees C, and I'm going to pass current through them. And these cables have losses, I squared R. So this thing will heat up. The cables will heat up. They will heat up above the ambient condition. They're already at 50 because of being in 50 degrees Celsius ambient. Then they will heat up another 50. They can melt down the insulation. Right? So everything, all electrical apparatus really has a limit based on physics, and I think we discussed it in 438, even power devices. Everything has, electrically, everything will break down because of physical phenomena, like voltage in this case, which needs insulation, which because of the breakdown of the dielectric, and heat. Right? So generators are the same. Generators, what will be the effect of heat? The heat is the current flowing through these windings. Right? So there will be a limit on how much armature current the generator can supply. Right? So armature current is this. Right? This armature current will cause some voltage drop across the impedance of the generator. I ignored the resistance here. But this armature current will have a maximum value, meaning this voltage drop inside the generator should be a maximum value. Otherwise, all this heat inside the generator will raise its temperature to a limit I cannot control. So there is a limit due to maximum armature current that I can sort of draw around this radius here. So I can sort of take this point as the origin, and let's say, this is, I didn't draw it very nicely, but there's a limit to this voltage drop, right? So this will always be where this voltage drop will start, right? Because this is the end of, this is Vt. So I will always add the voltage drop to here. So, and the length of this, or the radius of this, depends on the maximum value of armature current. Armature current will have a maximum value because all this voltage drop is inside the machine. It will heat the machine up. So that's one thing. How about another thing? The other limit. We said it's voltage, right? What voltage? Voltage that's generated internally in the generator due to what? Due to the field current, right? So I change field current, this voltage changes. So this voltage is this E voltage here, and it will also have a limit because I cannot keep increasing this forever. I cannot increase voltage forever, right? I will have to make sure that I insulate and the breakdown voltage is not reached. So this voltage will also have a limit. Assuming this voltage limit is this one, E2, then I will have another radius here, for example. Right? So this is the E limit, which means it's also the reactive power limit of the generator, right? And then this is the I armature limit, right? Which means it's also what? It's going to be closely related to how much power you deliver as well, right? Armature current is what you're delivering to the load at the end of the day, right? So these limits, I have to operate below this, and I also have to operate below this. And they intersect, right? So you will have to operate within this and within this one. Right? So a generator will have a capability curve. And of course you can, this is all voltage current, right? Voltages and currents, right? You can take this and now draw the same thing on an active reactive power curve, because you have your voltages and currents as magnitudes and angles, right? So I mean, I can take this voltage here and change its angle, right, which will correspond to reactive power changes here. So let's draw one with a new reactive power. Sorry. So anyway, do we get this idea of operation limits of a generator? So every generator will have operational limits, right? Besides the 90 degrees. Remember we said that power cannot, the angle cannot exceed 90 degrees. That's one thing, which means angle of what? Angle of E. So if I want to supply, so E can change here. For the if I want to continue delivering the same constant power that I was delivering, constant real power, then I can move E here. If I move E here, what did I do? This is my new E, for example. What happens here? Yeah, so I changed theta. So basically, basically E is the summation of Vt and the voltage drop, right? So now this, I actually have a smaller E than my V. Where do you think my current is? Is it close to V? But it's leading. It's a leading power factor, so you can draw something perpendicular to this, I guess. So this current is perpendicular to this voltage drop. So the current will be perpendicular to this voltage drop, and it will be, I didn't draw it nicely, but let's say I have a current that is here, right? So if this is my armature current, IA, right? Then perpendicular to IA is this voltage drop here, right? So this is now nu theta with a leading power factor. So anytime you have a leading power factor, your voltage, your internally generated voltage, is going to be less than your terminal voltage. Do we agree? Okay. And this is due to what? Due to having a leading power factor. So that's not purely due to the leading power factor. It's due to the magnitude of the current at that leading power factor. Right? If I have a small magnitude of current, if this current was small, then this voltage drop will be what? Small. Right? If this current was small, then the voltage drop will be small. Then E will be somewhere here. Correct? E will be somewhere here. I didn't increase delta too much, right? But what's happening now is I'm increasing delta too much. I'm not even increasing the real power, right? I'm actually supplying the same real power. I increased delta too much, close to my transient stability limits, which is somewhere the generator doesn't like to operate, right? So the generator, and what's happening inside the generator? How do you decrease E physically in the generator? You have, remember, field winding. You have a field winding across on the rotor, one on the rotor. All you can do is control the current, right? You control the current, it will control the voltage induced across the stator windings. That's all you can do, right? So how do you do this? How would you decrease? Here, E changed in magnitude. I decreased E. How do I decrease E? For me to decrease E, I decrease I, right? What happens if you keep decreasing E? You keep decreasing I. If you keep decreasing E, you keep decreasing I. At some point, you don't need, theoretically, you don't need any more current in the field winding to be able to have voltage on the terminals of the generator because of all the reactive power. Remember, reactive power, capacitors, what do? They change the voltage. How they change? They supply the reactive power locally to the load, meaning there's no voltage drop anymore across the line. So if the voltage was low, it actually increased the voltage because there's no voltage drop anymore. So now it's amazing because at the terminals of the generator, you have a high voltage but you're not controlling it, because you're actually not controlling reactive power anymore because you turned off your field winding. Right? So the field current is, you turned it off. The AVR, the voltage, the field winding control circuit is called AVR. It's called automatic voltage regulator. Right? These automatic voltage regulators is a power electronics circuit. It's a power electronics circuit that controls current, basically, right? So the AVR controller is going to turn off. The AVR's job is to, theoretically, is to be able to increase the leading power factor has higher E than V, right? So your job was to keep, control this current in the field winding. But now you're telling it, okay, no, I'm not gonna decrease, I want to decrease the current. Fine, I will allow you to decrease it. So generators can operate with a leading power factor. But okay, but don't push it. Okay, I allow you to increase it, but don't push it too much, right? Don't keep pushing leading power factor reactive current into the generator. Otherwise, I will not be able to control anything because I'm basically turning off the current in the field winding, and I have no longer control over E because my delta is going to be very close to where I don't like it to be, and I don't have any control. There is no mechanism of control. I will fall out of synchronism in that case. And I will end up with voltage across the windings as well. So there's going to be an over voltage across the windings because you're not in control of the voltage, the system is. You have no input because you turned off your voltage control system. Right? So generators don't like to operate in leading power factor because of that. And I added a link, some links at the bottom talking about that. And this specifically happens when you have IT systems, when you're feeding a data center. This is a very nice report. Go through it. It's a really nice report. It talks about data centers, right? Typically, all loads are lagging power factor, but a data center is computers. It's all electronics. Power electronics people know that everything likes to be leading unity power factor. So fine, we can make everything unity power factor by power electronics. But in doing that, we have to use these power converters that have input capacitors everywhere. So what if I decrease the load on the UPS? Or decrease the load on all these I turn off everything that I have. I still have the input capacitors, right? I still have input capacitors in the system. You read through it in detail. It's fun to read, actually. Fun, okay, for me, it was fun to read. But you have these input capacitors everywhere. Whereas you have these input capacitors everywhere in power electronics, right? Because you have these input capacitors, they're causing all this leading power factor. If you have a utility like Qatar Petroleum, you're feeding your Karamat power got disconnected for some reason. There's a disruption there. What's going to happen? You're going to turn on your generators, and your UPS system will kick in first. You will have no problem. UPS will feed everybody, and then as soon as your standby generator comes on board, you will probably turn off the UPS because you're fine. You have your generator coming on board, no problem. Everything is fine now. But this generator is going to see all these leading power factor loads. If it sees these leading power factor loads, because if you look at the report, these capacitors are there. These capacitors are there because you need them to power factor correction in the electronics. How about if I turn the electronics off? The reactive power in the capacitors is no longer used to feed the load. It's actually used to push leading power factor into the generator that you have on, that is the standby generator. And the generator will see over voltages and will shut down. Right? So it's very nice to understand this. I mean, I hope you like the idea of what's happening.